Here we go. Let's solve some initial value problems in the form of x prime equals ax. So these are systems of homogeneous differential equations. So first up, we have our x prime equals ax system with an initial condition here. And first off, we are going to need to find our eigenvalues because our solutions for all these problems, and I'll only really write it once, is x of t, that's a terrible t, is c1 v1 e to the lambda 1 t plus c2 v2 e to the lambda 2 t, where v1 and lambda 1 are a corresponding eigenvector-eigenvalue pair, and same for v2 and lambda 2. And then, of course, we can find our c1s and v1s from our C1s and C2s from our initial condition that's given. So let's find our eigenvalues. We'll be solving the determinant of a minus lambda I equals 0. That will be 3 minus lambda times negative 1 minus lambda plus 4 is equal to 0. Lambda squared minus 2 lambda. Is that right? Minus 2 lambda minus 3 plus 4 is plus 1 is equal to 0, or lambda plus 2 lambda minus 1 times lambda minus 1. So we have an interesting situation here where we have a repeated eigenvalue. So our solution is lambda equals 1 with a multiplicity of 2. And so plugging in lambda equals 1 to our a minus lambda I expression, we can solve for the corresponding eigenvector. That will be subtracting 1 from the main diagonal, so 2, negative 2, 1, negative 4. And what's happening here? Well, we can simplify this down to 1, negative 2, 0, 0. This says x1 is equal to, if we move the negative 2 over to our right-hand side, to x2. So we can get an eigenvector of 2, 1 out of it, if this is an eigenvector of, or a vector composed of what x2 is equal to. It's equal to 1 of itself, and 2 of it is equal to x1. Okay, either way, we have our eigenvector now, so we can start writing out x of t is equal to c1 to 1 e to the 1t plus c2, but we have a little bit of an issue here because we have a repeated eigenvalue, so we don't have a different v2. So what we're going to need to do is add our 2, 1 with a t on it, and then we need to find a generalized eigenvector here, and that will be from setting up the system, the augmented matrix of a minus lambda I, so 2, 1, negative 4, negative 2, and then 2, 1, our eigenvector on the other side. Simplifying this down, we get 1, negative 2, 1, 1, negative 2, 1, so we can zero out this entire row. And this right here is our generalized eigenvector, what we get on that side. So 1, 1, 0 will go in there. Now all we're doing is solving for our initial conditions here to find c1 and c2. So we can plug in t equals 0 and set x of t equal to 1, 0. And that's equal to c1 times 2, 1 plus c2 times 1, 0, because this t will be 0. So we can set this up again as an augmented matrix. 2, 1, 1, 1, 0, 0. Solving this, we see that x1 right off the bat is equal to 0, and c1 is equal to 0, c2 is equal to 1. So this entire term is just gone. And now finally, we can do what we came here for, which is solving for x1. So x of 1 is just 2, 1. We need another bracket there. 2, 1 plus 1, 0 e to the 1. So that gives us 3e and then e as our answer. Continuing on with number 20, we're considering this differential system, which is just another x prime equals ax, and we're finding the set of fundamental solutions. So that will be our C1 times our first fundamental solution plus C2 times our second fundamental solution, where in here we have our V1 e to the lambda 1t, V2 e to the lambda 2t. But because we're getting three solutions, or actually two solutions, but you'll see we have some multiplied by t, some not in here, we're expecting to get some multiple eigenvalues to deal with yet again. So solving a minus lambda I equals 0, 1 minus lambda, that's an x, 1 minus lambda, negative 7 minus lambda, plus 16 is equal to 0. This gives us lambda squared plus 6 lambda minus 7 plus 16 is plus 9 is equal to 0, or lambda plus 3 squared is equal to 0. So lambda is equal to negative 3 with a multiplicity of 2. Plugging in lambda equals negative 3 to a minus lambda I, we will get 4, negative 4, negative 4, 4. We'll simplify this down to 1, negative 1, 0, 0. And since this says that x1 is equal to x2, we can write our eigenvector of 1, 1. So moving on now, we have our v1, and our lambda 1, but we're going to need to find our generalized eigenvector to be able to find our second solution, because we have our first solution here. We can write it out. It's 1, 1 e to the negative 3t. So finding this generalized eigenvector, we're going to be solving a minus lambda I equals v1, so that's this augmented matrix here, with our 4, negative 4, negative 4, 4. And so, we can simplify things down. We can subtract row 1 from row 2. That will zero out everything there. And then divide this all by 4. 1 over 4, like so. And once we have it in the same form as the form that we use to solve, you'll see these 4 are the same as these 4. It's in the form that we use to solve for this first eigenvector. This on the left side, sorry, that's the right side. On the right side is our generalized eigenvector. So this is x, well, they're putting it in the exponent, I'm not sure, x1, and x2 is going to be 1, 1 t e to the negative 3t. Remember, we have to add that t because we need to use our generalized eigenvector in here as well, plus 1/4 0 e to the negative 3t. And looking around quickly, that seems to be answer choice C. 19, let's find the solution to this initial value problem. So yet again, we're solving the determinant of a minus lambda I equals 0, negative 4 minus lambda, negative 4 minus lambda, minus 4 is equal to 0, or lambda squared plus 8 lambda plus 16 minus 4 is plus 12 equal to 0. Let's see, how can we factor this? This is lambda plus 6. Lambda plus 2 is equal to 0, or lambda is equal to negative 2 and negative 6. For lambda is equal to negative 2, a minus lambda I will give us negative 2, negative 2, 2, 2. We can simplify this down to 1, negative 1, 0, 0, and pull out our eigenvalue of 1, 1, because this top equation can be rearranged to say x1 is equal to x2. So there's our first eigenvector. For lambda is equal to negative 6, a minus lambda I will become 2, 2, 2, 2. Simplifying things down, 1, 1, 1, 1. So we get an eigenvector of negative 1, 1. We are almost done here because we can say that x, that's a c, x of t is equal to c1 v1 e to the negative 2t, that's lambda 1, plus c2 v2 e to the lambda 2t, which is negative 6t. And using our initial condition here that x at 0 is 1, 0, we can solve for c1 and c2. So 1, 0 is equal to c1, 1, 1 plus c2, negative 1, 1. So we can set this up as an augmented matrix, 1, 1, negative 1, 1 is equal to 1, 0. Let's subtract row 1 from row 2. We will get 0, 2, negative 1. Let's divide this 2 out, and then add row 1 to row, add row 2 to row 1. 0, 1 half. So we see, whoops, I erased things by accident, plus negative 1, 1, e to the negative 6t. There we go. We see that c1 is equal to 1 half and c2 is equal to negative 1 half. It looks like they have factored this negative 1 in here, so we will do that as well, and we are left with option, not option C, they have the 6 in the wrong spot, option E. Yep, that looks good to me. 19, let's find the general solution to this thing right here. We're expecting to see some repeated eigenvalues because we have this whole double bracketed thing with a t and a constant, blah, blah, blah. So that we should expect to see that in about a couple minutes. So we're solving negative 4 minus lambda minus 8 minus lambda plus 4 is equal to 0. Lambda squared plus 12 lambda plus 32 plus 4 is plus 36 is equal to 0. So lambda plus 6 squared equal to 0. Lambda is equal to negative 6 with a multiplicity of 2. So we would hope that when we find a minus lambda I for lambda equal to negative 6, which is 2, negative 2, negative 1, 4, we would hope that we get 2 free variables here so that we'll get 2 eigenvectors out of the deal. But that, I don't know even if that can happen at all in 2x2 systems. It almost never does. Never does, actually, in exams. So we can simplify this down to 1, 2, 0, 0. x1 is equal to negative 2, x2. So we get an eigenvector of negative 2 and 1. Negative 2, yep, negative 2, 1. That looks good. So moving on, we will need to find our generalized eigenvector, because currently our solution has the form x of t is equal to c1 e to the negative 6t times v1, negative 2, 1, plus c2, and since we have a repeated eigenvalue, we need our first eigenvector times t plus our generalized eigenvector, which currently we don't know, e to the negative 6t yet again. This generalized eigenvector we get by solving a minus lambda I is equal to v1. So that is 2, 4, -2, -1, -2, 1. Dividing things by 2 up top here, we get 1, 2, -1, and we can add row 1 to row 2 to zero all of this out. Then once we have things in the form that we were using up here on the left side in our augmented matrix, the right side is our generalized eigenvector, so we can put -1, 0 in there. And now we're asked to identify which of these, well, tried to explain that in a cool way. No, we just picked the correct answer here. So we're looking for -1, 0. It looks like they have flipped the sign of all of our vectors, which is perfectly fine to do because remember that C1 and C2 can be any real number. So those being negative would adjust for that perfectly fine. So let's flip all of our values to match what they have there. And I'll just try to find this quickly. It looks like E matches. Yep, E matches everything that we found. 18. The real 2 by 2 matrix A has an eigenvalue, lambda 1, of 3 plus 2i, and the corresponding eigenvector given there. We're finding the general solution. So what we have to do here is set up v1, 1, 2i, times e to the lambda 1, 3 plus 2i t, and kind of do some moving things around and substitutions, and we'll end up with something that is real and has two parts of it. Believe me, it'll make a lot more sense in a second. So I'm going to split this up to e to the 3t plus I 2t. We can split this up some more, make this into another e to the 2it, and then we can replace this 2it by Euler's identity with cosine 2t plus I sine 2t. And now really what we're looking for is the real portion of this when we expand it out and the imaginary portion. We will find both of those, take off the I, replace the I and the constant out on the left with C1 and C2, and we will be good to go. So finding the real portion, that will come when we multiply cosine on top and sine on the bottom. So we have C1 cosine 2t minus 2 sine 2t, because I squared will give us -1 times e to the 3t plus C2 times the imaginary portions. That'll be cosine multiplied on the bottom and sine multiplied on the top. So that's sine 2t on top and 2 cosine 2t on the bottom, e to the 3t. Don't want to forget that. And we are done. Where is our answer? Our answer is C. 19. Given that x equals e to the negative t times beta 2 is a solution to this, we are finding beta. So let's find x prime. That will be negative e to the negative t beta 2. And before we plug everything in, we're going to make our lives a little bit easier by recognizing that since every term, once we plug it in, will have an e to the negative t in it, we can just imagine that those do not exist at all, because we could just divide them out in the end. So I'm going to completely cross that off, I have to remember that this negative sign still does exist though, and we'll plug things in. We get negative beta negative 2 is equal to negative 3, 5, negative 2, 4 times beta 2. Expanding this out into two equations, we have negative beta is equal to negative 3 beta plus 10, and negative 2 is equal to negative 2 beta plus 8. Since we only have one variable to find and two equations to do it with, and we know that this solution does work, both of these equations are equal. They both determine the same value for beta, so we only have to use one of them. We'll rearrange equation 1 to say 2 beta is equal to 10, or beta is equal to 5. That's 8, 5. 17, let's find the general solution to this system right here, solving determinant of a minus lambda I equal to 0, 2 minus lambda, negative 4 minus lambda, minus 7 equal to 0, lambda squared plus 2 lambda minus 8 minus 7 is minus 15 is equal to 0, lambda plus 5, lambda minus 3 is equal to 0, lambda is equal to 3, and negative 5. Plugging in lambda is equal to 3 to a minus lambda I, that will give us, for lambda is equal to 3, negative 1, negative 7, 7, 1. Simplifying this down, 1, negative 7, 0, 0. So we get an eigenvector, 7, 1. For lambda is equal to negative 5, a minus lambda I will give us 7, 7, 1, 1. Simplifying that down, 1, 1, 0, 0. And so our eigenvector is negative 1, 1. That's a 7. Negative 1, 1. And we are good to go. We can say that x of t is equal to c1 v1 e to the lambda 1t plus c2 v2 e to the lambda 2t. And that should be one of our answer choices up here. It looks like C. Sorry, I'm a little tired. D matches that perfectly. Okay, yeah, we're done.